All right. So far, we have looked at the basic algorithm for graph neural networks, essentially the neural message passing step, where it is consists of two core steps. The first step is to aggregate information from the neighborhood of each node and construct a message. And the second step is to combine this message with the current embedding of the node using an update function and construct a basically updated embedding for this node, right? So next, we looked at some methods to enhance our basically aggregation and update steps. For instance, we looked at, improving the quality of our embeddings, overcoming over smoothing, and so on and so forth. Adding essentially fully connected layers before and after each embeddings in order to come up with more richer embeddings. So now there are in general four famous architectures that people use for to implement graph neural networks, and we are going to review this, which elements of which we have looked at so far. So these four include first graph convolution network, known as GCN, then graph sample and aggregate, known as graph stage. Then we have graph attention network, shown with GAT. And then we have graph isomorphism network, known as GNN. We'll start with the first one. So in the graph convolution network, again, we're just looking at the two steps. There are just some variations in the two core steps, but basically all four of these contain aggregate and update steps. So in GCN, the idea is that in the messages are constructed by a mean function as our aggregate function, which takes the information from the neighborhood and normalizes them by the square root of the degree of the node itself and its neighbors. So also it contains self loops, meaning that our sum is over all the neighbor nodes plus the node itself. Then in the update step, it is using a single layer fully connected network. So it takes these messages and it multiplies this using it basically with some weight matrix and applies some nonlinearity, and then it has its output. All right. So the next one is graph stage, in which we have improved the graph convolution network by making the aggregation trainable. So aggregate has some weights of its own. It applies those on the input embeddings, and then it applies some basically multi-set aggregation function. Here, the function that we use for aggregation is max pooling, which is element-wise maximum of the different input vectors that we have in our multi-set. So it goes through the first dimension of h's for everything. It just finds the maximum of that, and so on and so forth. And then it constructs the messages for basically each node. Another thing that it basically graph stage has is neighborhood sampling. So we said that we don't, in neighborhood sampling, the idea is that we don't want to include all the neighbors in each iteration. We just sample, for instance, let's say that the maximum of k or t, whatever, neighbors at each node. So the number that they have in two layers is 500. So the total number of the neighborhoods in the first iteration times the total number of the neighbors in the second iteration should be less than or equal to 500. So then in the update step, what they do is that, so they didn't have an explicit self loop there, but they concatenate the messages that they aggregated in the previous step with the embedding of the node VI. And then they pass that through some basically single layer fully connected network, right? So that's gonna be the update step for graph stage. Another method is graph attention network, which basically introduced the idea of attention in the graphs. So the idea is that not all neighbors of your node have the same importance. So it introduces some parameters in order to learn which nodes are important. So it basically introduces some directional bias when computing, when basically aggregating information from the neighborhood. So for that, it needs some attention mechanism, which is a function that returns some coefficients representing how important different neighbors are. To compute that, in this basically graph attention network, the model that they have used is that they pass each embedding through a single layer, linear, basically layer without non-linearity. So in order to improve the input embeddings, they concatenate the embeddings of the two ends of each edge in order to construct an embedding which represents each edge in the neighborhood. Essentially each edge incident to node VI, and then they implement a single layer neural network which has essentially parameters A, which is a vector, and some nonlinearity. It is vector because it basically takes some input of size, basically whatever each of these are, times 2, and then it returns a single value, a scalar value. So now we have our attention mechanism defined. We can compute these coefficients for every edge in the neighborhood. And then we need to normalize this using some basically normalization method. The one we use here is softmax. So we pass these through softmax in order to turn them between values that sum to 1 and between 0 and 1. And then we use a summation as our aggregation. And in this summation, we multiply the embeddings of each neighbor, Vj, by the normalized attention coefficient that we computed through this attention mechanism. Now using this, we have constructed the message, and then we pass this message to our update equation, which is again a single layer, fully connected neural network that has basically parameters W. And these are essentially the same as W's used in the aggregated iteration before. So then this value HI represents your embeddings in the new iteration. And lastly, we have a model called Graph Isomorphism Network, or GN. The idea with this, essentially the paper that presented this, is to build a neural network that has maximum expressiveness. And for that, they have introduced, so they have used sum as the aggregate operator, which is just summing over all the neighborhood embeddings. And then they have introduced a parameter epsilon at each layer, which shows how important is our target node in comparison to its neighborhood. So we have some messages coming from our neighborhood. We have some information basically residing on the node in the current step. And then in the update, we want to just add them together to combine them together, right? So if I have epsilon equals 0, that means that our H and our M are of same basically importance. So they go ahead and basically say that their best performance achieves on epsilon equals 0. So it doesn't really improve their network. But what happens is that in some graphs, setting epsilon equal to 0 doesn't differentiate between some specific types of graphs, and that's the idea. That's the idea with expressiveness. You want to build something that can easily distinguish between different graphs. So they have kept this in because it helps in some scenarios, but not generally speaking. And they have multiple tests with epsilon fixed to some value or epsilon as a learnable hyperparameter. So then they say that just passing that through a single layer of neural network is not enough. So they have a multi-layer perceptron as their update equation, which takes this basically a combination of the messages and the current state of the node, and it returns the basically updated nodes embedding.
All right, so so far in the last session, we discussed about 4 different types of graph neural networks, including GIN, GAT, GCN, and graph sage. There's one common point between all these methods, and that's the fact that they are working on a node level. They are propagating information on a node level. So that means that, let's say that you're applying some graph neural network layer on this graph. Let's say that we want to update information, the embedding on this node. In the first step, you're gathering all the information from its neighbors. Then that's mathematically good. That means that we have some aggregate step that basically gathers the information in the multi-set of all the neighbors of the embeddings of all the neighbors of this node, and then turns them into a message. And then we take this message in the next step, combine that with the current state of the node, and then we turn that into a new embedding. So that's done in a step called update step. So next, we're gonna consider the fact that in many graphs, node embeddings are not all the only information that we have in the graph. We also have edge level information and we have graph level information. And we would like to incorporate those into our graph, basically embedding, right? So we want to incorporate that into our problem as well. So, so let's say that we have this graph. Now, in the previous problems, we were only considering our node embeddings. Now, we also have embeddings corresponding to all the edges in this graph, and we have one embedding corresponding to the whole graph. So now we would like to apply a method that generalizes the graph neural networks, meaning that not only it performs basically gathers information on the node level, it gathers all the information on the, as well as node level, it gathers information on the edge level, and it gathers information on the graph level. So let's say that, for instance, we would like to find an embedding for this new embedding for this edge. For doing that, we're gonna look at the neighbors of this edge, 2 ends of this edge, which are nodes 1 and 6. You're gonna look at the previous state of this node, which I'm showing here with hk-1 sub 1 6. So again, we're gonna gather information from basically its 2 ends. And then we're also going to combine information from the basically graph level embedding in order to update the embedding for this edge. Now we're going to write that using an update equation for the edge that gathers information mathematically put from for a basically edge ij. It's going to gather information of embeddings of node vi, vj, the embedding for the graph j, and the embedding for the edge itself in its previous state. So next, we're gonna look at how this gathers information. Basically, it updates information on each node. Let's say that we want to find the updated embedding for node 1. I'm going to show that with H1K, K meaning that the output K. So I'm going to take information as at basically previous level K minus 1 for this node. So the information that I'm going to use are threefold. First, I'm going to gather all the information from the edges that are incident to this node, right? And that's going to be the information that we just updated in the update edge step, right? So I gather all this information. Then to these, basically, I'm going to add 2 more information. But just adding the information on the edges is going to construct my aggregation step for this node. So we construct a message using information on the edges. And then we take this message along with the previous state embedding of this node and along with the previous state of embedding of the whole graph. And then we're going to combine that into a updated basically embedding for this node. Mathematically put, we're going to show that using an update node operator, which takes basically 3 sets of information. And it's going to combine this into a updated embedding for node VI. Next, we have the embedding for the graph that we would like to update. So for this, so far, we have updated the embedding for all the nodes in the graph. We have updated the embedding for all the edges in this graph, right? So we just construct a multi-set of all node embeddings. And then we construct a multi-set of all edge embeddings. And we add to that the previous state of the graph embedding. And we are going to combine all those using an operator called update graph. And we are going to combine them in order to construct an updated embedding for the graph. So that is basically how our generalized message passing algorithm is going to look like. We looked at jumping knowledge connection, which was concatenating all the information, all the outputs of different layers into one vector, and was basically using that as some basically output representation for the nodes. Then we said that, all right, node embeddings, node basically classification type of problems is not the only problem that we're going to deal with. We are going to also deal with problems that are in graph level. So we need to kind of gather all the node embeddings that we have constructed into one graph embedding. And we were using 2 set of approaches for that. First of all, we have multi-set pooling, which was essentially like the approaches that we used when we were gathering information for each neighborhood. Like for instance, summation or maximization, element-wise maximization. Then we have graph coarsening, which was basically inspired by CNN models, convolutional neural networks, and it was at each graph neural network layer, after each graph neural network layer, it was trying to generate a coarsened version of that graph and kind of try to combine information on each clusters that it was basically gathering nodes to generate the coarsened graph. And then we reviewed, of course, some popular graph neural network models. And lastly, we looked at general message passing approach, which was trying to integrate information from node edge level and as well as those on the graph level.